Can everyone hear me?
Hello?
Hello.
Yeah. So it's probably this is my problem. Okay, you can start.
Oh, okay. So I'll start my presentation on FIXREVERTER, which is a realistic bug injection methodology to test the fuzz testing, the fuzzes, test the fuzzes. So these are the 4 authors for the paper.
So maybe you can briefly introduce the authors, because maybe one day you go to a conference, or some of our PhD students go to a conference, they will have some impressions on some of the authors.
Oh, okay. So the first author is Cheng. He's a PhD student at University of Texas, and his interest is in cybersecurity and fuzz testing and static analysis. And another author is Professor Fix Patterson. He's also from University of Texas at Dallas, and he's interested in data collection, geographic information system, and as well as statistical analysis. The third author is Professor Michael Hicks. He is also a senior principal scientist at Amazon, and he is interested in software availability, reliability, and cybersecurity. And lastly is Assistant Professor Sui Wei, also from University of Texas at Dallas, and he's interested in practical ways to do program analysis for software reliability and cybersecurity.
Okay.
Right, so some background on fuzz testing. So fuzz testing or fuzzing is an automatic way to do software testing by providing invalid or random data as inputs to a computer program. And then we will monitor the program for crashes and some memory leaks. So this is often applied in cybersecurity to find vulnerabilities in code. And fuzz testing is an active area of research, and many improvements are published at a very fast pace. So having a benchmark that we can test these new improvements on is very important.
Okay, so maybe you can raise the question. So first, anyone can well describe what is fuzzing. Have you ever heard of a fuzzing before? So any volunteers for the fuzzing? Yeah. Okay. So Cheng, maybe you can have. Do we have a definition in your slides on the fuzz testing?
Yes. So definition is basically to provide invalid or random data into a computer program, and we monitor it for crashes. So that's fuzz testing.
So I think we have students like Zhang Yi, Yun Rui, and Cai Yi, who would work on software testing. And here the topic more in the security are called fuzzing, because in software engineering, we usually have available source code, and every program structure are quite transparent. But for securities, we're looking to binary code. Of course, we can still pass in the code structure of the binary code, but usually the input is very, so the input usually could be a PDF, could be a string, could be a message, could be everything. So in this case, the semantics of the target program is somehow unclear. In this case, we will try to randomly generate a lot of the input. This input, just as Cheng mentioned, it could be a random number, but more often than not, it could be a random file. It could be a random program, or it could be a random string. So that one is observed, giving those randomly generated input, and whether the target program can crash or have some unexpected behavior. Okay, is it?
Okay. I have a question. So, because we are not looking at any particular unit to test, right? We are looking at the software as a whole. Am I correct to say that the fuzz testing or fuzzing is more like an integration test or a system test?
Exactly. So for software testing, we have unit testing, and one level up, we will have integration set testing. So this fuzzing is more like system testing. So we test the whole program as a whole. So what we can observe is the input, the program input. what we can offer is a program input, and what we can observe is a program behavior like crash, and that's all.
Okay. But then let's say if a program crashes for a given fuzzing like test input, how do you know which part is causing the problem because you're only looking at the binaries?
Yes, so we need to separate two problems. The first is about the bug discovery or vulnerability discovery. And second is about the root cause analysis. So as long as, so the problem is, for example, if we have companies, if we want to deliver some very important programs, we wanted the program out of bugs, right? To clear
Yes.
bugs. So this is the first step. So the first question is whether there's a bug. And then we answer where the bug and how to fix the bug. And
Okay,
for software testing, we just answer the first question.
Okay, okay, I get it. Yeah.
Okay, great question. Okay, I think we can move on.
Okay. So this paper referenced another paper which talked about how we should create a benchmark to test different fuzzes, and they specified 4 different goals for the benchmark. So the first goal is that the target program has to be relevant and realistic. The second goal is that the bugs has to be also realistic and relevant. So in this case, relevant bugs will mean the bugs that fuzzers are supposed to find, like memory errors or crashes. And the third goal is that the bugs has to be triggerable in a way that we can know which bug was triggered. So we don't double count the bugs. If let's say the bug was triggered twice, we don't double count it. Then that will make the fuzzer look better than it actually is. And we also want to defend against overfitting, because some new improvements, when they release the experiments, they might use some heuristics to purposely overfit to the target program. So we want to avoid that as well. And the problem now is that many of the benchmarks don't satisfy all 4 goals. And this paper is proposing a new method that will satisfy all of them. So one example of a benchmark that doesn't satisfy all 4 goals is UniFuzz. So UniFuzz is a collection of benchmarks that contain real programs and actual bugs. So it satisfies the first 2 goals. But the problem is...
Sorry, so I have a question. Can you further distinguish the goal 1 and goal 2?
Sorry. Yeah. So goal 1 is relevant and real world target program, and goal 2 is realistic bug. Yeah.
Okay, so the goal 1 is the real target, and goal 2 is the real bug, right?
Yeah.
Okay.
Yep. So it uses real programs and real bugs, so it satisfies both goals for UniFuzz. But the problem is when they try to distinguish the bugs. So they use stack trees to distinguish. So let's say an example is calling a method causes a crash, but the method can be called from different places. So, but then the stack trace will look different, even though they're calling the same method. And this would cause a double count in the bug. So it doesn't satisfy a unique way to identify each bug. And also in general, many benchmarks cannot prevent overfitting. So one solution that previous researchers have thought about was to automatically inject bugs into an existing program. So this can try to prevent overfitting by generating new bugs in code. So one example of an automatic bug injection to prevent overfitting is Lava. But the bugs injected, for example, in the one on the image, is actually it's not realistic at all. So it doesn't satisfy G2. And also this kind of bugs, especially in Lava, is actually quite easy to beat, because one way to beat this is to scan the code for constants, and then we try the constants as inputs. So eventually it will be A equals to the constant, and we will enter the crashing code. So this is one issue with Lava. Okay, so given that there exist such problems, the paper is proposing an automatic bug injection tool that will satisfy all 4 goals, which I will explain in the first section, the FIXREVERTER. And they also created a collection of target programs called RevBugBench, and they ran FIXREVERTER on 10 programs. Then I'll talk about the experiments that they did. They took real fuzzers and ran on the RevBugBench programs. So they have some results for that. And finally, I'll end with some takeaways.
By the way, Cheng, Have you prepared a few questions that you can throw away during your presentation?
Sure, I can ask some questions. Yeah.
Okay, great. And also maybe a few of us can try to raise the questions to Cheng. I think particularly we can ask the one who is doing relevant research, like Cai and Zhang Yi. But definitely all the participants are encouraged to raise as many questions as possible. Yeah, just you think about it, in the future, you can attend an academic conference. People are presenting their work, but raising the question is very important and a critical component, right? So for these academic activities, and always we all know that FSC will be held in 2 months. So we hope that if you have a chance to attend a conference, I think most of us do, it's better for you to think of the questions. And since we are, most of us are juniors, so if you're students, it's okay that you can raise some naive questions. That will be no problem. Okay.
Okay, so this is the architecture diagram for the bug injector, which is called FIXREVERTER. So so first the system will take in something called bug fix patterns. So these patterns specify code. What kind of code should we modify? The syntax of the injection sites. And then the syntax matcher will use these patterns to find matches in the code, to find places to inject bugs. And the third step is to check whether that injected site is even reachable in the first place. And also whether the injection site, using data dependence, will it lead to crashes like null pointer exceptions, etc., from the bug injection site. And if all of these passes, we will actually inject the bug. And after injecting the bug, we will run those bugs to see if they are too easy to detect, and we'll filter them out. And we'll be left with relatively difficult bugs that we can test our fuzzes on.
And I have a question about reachability. And so there are a technique to make sure the injected bug is reachable.
Yes.
How could they? Anyway, so we're going to see the details later.
Yes. They use control flow graph and from the entry points. Yeah. So later.
Yeah, but the control flow graph is not necessary to guarantee the reachability. Okay, so maybe I raise the question here. Why we need a syntax matcher here for the whole workflow? And then volunteer try to answer the question. And then volunteer try to answer the question. Ifan, are you listening?
Yeah.
Yeah, so could you answer the question, why in this workflow we have a syntax matcher?
To check the reachability for the next step.
Sorry, I cannot hear you.
Oh. Maybe it's to check the reachability for the next step. So they need to
reachability. And then Xiaoling, do you agree with Ifan?
Sorry, the question again.
The question is, why do we need a syntax matcher in the whole workflow? And how about Yufan?
Maybe needed to put the bug in a proper position.
Locate the bug in a proper position. Yeah, that's something relevant. But how do we define the proper positions? Why it is relevant to the syntax? If it is a location, we can just using any location related heuristics, right? But why we need a syntax? Why syntax matter here?
Because because this is a bug pattern, so you need to put it on a proper, the same syntax on the code. If it's not, maybe the code can't work. I also don't know. I just guess.
Yeah, that's somehow relevant. Maybe Cheng, you can help explain, or do you agree with Yufan?
Yeah, so it's actually this actually is because of the way they create the bugs. So I will explain in detail later, but the way the bugs that they inject is based on CVEs. So CVEs have a buggy version and a fixed version, right? So they will look for the fixed version in the code, and then they will change it to the buggy version of the CVE. So that's why they use a syntax matcher to find matches to the fixed version. Then they'll change it to the buggy version in the CVE. So that's
I think,
why.
Yeah, I think you should take the context of what Cheng has presented. The idea is that we want to be realistic bug, right? So, but the problem is that they want to generate an artificial bug, which is very similar to the real ones. In this case, it will have to find some going to see what the real world bug looks like. That's why we need a bug fixing pattern. And once the pattern there, the patterns or the appearance of the code must have some syntax. That's why we need a syntax matcher to see in what areas is more likely to have real world bugs. And then they, as Yufan mentioned, then based on these features, they find where they're going to inject the bug. All right, is there any question here? Okay, if there's no questions, we can move on. Yeah, but we can throw out the question from time to time so that everybody can follow.
Okay. So from the previous overall flow, we can see that there's the bug fix pattern grammar, syntax matcher, the reachability and dependence analysis portion, as well as the final bug injection. And part 5 was actually not shown in the architecture diagram. So this is where they created an algorithm to find the root cause of a crash. So why we need this is because just because a bug was triggered doesn't mean that that bug caused the crash. So we have to find the exact bugs injected that caused the crash. So we need an algorithm to find it out. Okay, so
yeah, it's better to have examples here, because usually where we inject the code is a way to create a bug, right? But now you're saying that the root cause is not where we inject, is somewhere else.
They will inject many places, and if it crashes, we don't know which bug caused it. So they have an algorithm to find only those few bugs that caused it, the exact bug.
Oh, you mean that we can inject multiple bugs?
Yeah, they inject multiple bugs in different places, and they'll run the input on it. And if it crashes, it will use the root cause triage algorithm to find the actual bugs that caused it.
Okay.
Okay, so this is the bug fix patterns. So okay, this is a lot of this is just a snapshot. So I'll go through this in detail. But basically, it is a context-free grammar. And as explained before, the bug fix grammar specifies the syntax of the code that we want to find. And if it matches that syntax, we will change it to become buggy. So that's what the grammar is for, is to find places to inject the code. And this grammar is based off of the fixes for CVEs. And so CVEs have a fixed version and a buggy version. So after we match the fixed version of the CVE, we will convert it into the buggy version before the fix happened. So the researchers looked into 693 CVEs from 6 open source projects, and they chose these 6 open source projects because they were well studied for fuzzing. They also contained code diffs for fixes and bugs, so it was easy to identify the pattern. And they brought these 693 down into 3 distinct patterns that are easy to understand and quite general, which I'll explain in the next few slides. So the first pattern, yeah.
So here, this grammar is manually extracted from the CVE.
Yes, they manually looked through 693 CVEs and found a general pattern of these CVEs.
Okay, you can elaborate more later. Yeah.
Okay. So the first pattern that they discovered was quite, they appeared a lot was the abort pattern. And what abort is in summary, is a guard clause. So it checks if an object is null, and maybe an object is dereferenced after this, which can cause a null pointer exception. So abort in this sense means it will break execution flow. It checks if an object is null, and it won't allow it to be dereferenced later by breaking the flow. And the condition can consist of disjunction conditions. So this is an abort fix. The fix is to add this guard clause. Then for execute fix, if you look at the code, we can see that symbols is dereferenced at line 9, which can cause a null pointer exception. So the CVE fix was to add symbols not equals to null before executing the body. So this is different from abort because the previous slide, the abort, because this is not a guard clause. It makes the condition tighter before executing the body, which is why it's called execute.
It seems there's no difference, right? So so we can just rewrite the code into symbol not equal to null and return.
Simple not equals to null and return.
Or yeah, so I think the executor phase fix and abort fix both going to check a condition. If this condition has been satisfied, it will change the control flow, right?
Yes. But for
And the first one, the control flow is that we leave the method as soon as possible. And for the second one is that if it's not if the condition is satisfied, we will not execute a piece of code. And from a philosophical point of view, it seems exactly similar to me.
I think it makes the condition tighter though before executing the body. For execute, it adds an additional condition.
Yeah, I
before running
understand.
a
So
body.
these additional conditions can be rewritten to add a new condition, right? We're not necessary to put these conditions with a conjunction. We can rewrite these forms into an additional condition expressions, right? Focus, and we maybe in this case we can add a new if condition block hosting the original block, right? They are the same from a semantic point of view.
I see.
Yeah, I understand they want to have a good detailed taxonomy, but from the point of program analysis, they're equivalent.
I see. Another difference I think might be for execute, they allow while and for statements. But this one,
I understand. So they're talking about the syntax patterns and how do they fix it, right?
Yes.
But from the semantic point of view, it makes no difference to have additional if condition, or we add a new conditions in the if expression, in the if condition expression.
I see.
Because from a program perspective, I don't. Yeah. So if it is a bug, it can happen. Anyway, it will happen anyway. It doesn't matter about syntax, right?
I see.
Okay, let's move on now.
Okay. So the final pattern is assign. So it fixes a value assigned to a variable. So for instance, in this fix was that s could have been larger than max possible value. So we change it to max to prevent perhaps like a array out of bounds error. So this is an assignment. Yep. So if we go into the context-free grammar, we can see what I explained before is available. So if statement, it only allows if statements followed by disjunction conditions. And the abort body must contain a jump statement to break the execution flow. And what I thought was interesting was that it allows only up to 3 statements before jump. And I believe this is because if we skip the entire block and the block has many statements, it is too easy for the program to fail. So they don't want the bug to be too easy to be detected. So when they skip an entire guard clause, they don't want it to have too many statements inside, which can make it too easy to fail. Okay, for execute, so as I explained before, it's also if, while, and for statements, and it's followed by conjunction conditions. And the body must not have any jump statements as well. Yeah. And lastly, for assign, it only must have a single condition, and there must be an assignment in the body. And the assignment body is so here we can see tracer.
Yeah, so here I got it. So it is using some fancy grammar. So this is basically a BNF format to define different languages. But the point is that it shouldn't be. I think it could be a learnable program. They collected over 600 fix, and there must be a way to using some machine learning technique to automatically summarize instead of manually define those rules.
I see.
And this, so is that, and how many patterns do they summarize?
Only three. These three.
Only three. And how these patterns can cover, and how many of the CVEs can be covered by these three patterns?
Out of 693, they filtered to, I think, 200 or 100.
200, which means that 1/3 to 1/6 to 1/3 of the bugs fall into these patterns. And how about the rest?
The rest, they did not talk about them. They just said that I assume it's because they're too complicated. They want to use a simple general one to maybe make the explanation easier for the people.
Yeah, so it's too simple, I guess. Okay, let's move on.
Okay, so in the grammar, they can actually specify something called tracers. So what tracers are for is to check whether the object will be dereferenced later. Because even if you remove the guard clause, even if the object is not dereferenced, it won't result.
I got it. Yeah.
So
So they just want to have maybe use after free, maybe and the non-point dereference bar, right? So they want to synthesize this kind of.
Yes, they want to track the object. They want to track this, whether it will be used later.
Okay.
Yeah. So this is a syntax. Yeah. So this is a syntax to specify what variables to trace. So the first pattern, this one is not used, so maybe I'll skip this. But the second one is, second one is this one. So you can see the object, it matches this one, pointer var, trace var, the first one. And so this means that we will trace object into the array trace bar. We will store all these objects into an array. So it told the program to check all these variables in this array for dereferences later.
Okay.
And they will store this in a JSON form. Okay. So next is the syntax matcher. So they split into two phases. So they first create a state machine using the bug fix grammar I mentioned before. And then later they will create an AST. And as they traverse down the nodes, they will go through the state machine as well to find matches. Okay, so to create state machine, they use an LR0 parser to create it. And whenever multiple paths can be taken in the state machine, they will fork the process. And each of them will try different paths. But if multiple matches are returned, it will fail. So we need to specify a grammar that are mutually exclusive. It can only end up in a single pattern. So this might be a bit difficult, but yeah, they need to be designed this way.
So this is a state machine, right, Cheng? Is there a graph for how the state machine will change?
State machine will change. What do you mean by change?
Oh, correct me if I'm wrong, because I'm under the impression that the state machine will basically tell us how the state change when we find something like new, or when we find something that is relevant. So by looking at these four rules, like four lines of text, I can tell how the state will be modified or be changed. Let's say when we are seeing if multiple paths.
My understanding is that there's no change. So let's say the state machine in this case would be like if we enter if.
Maybe I can briefly introduce the rationale. So this is part very similar to the lexical analysis in the compilation principle, but I don't want to using too many of the terminologies. You can just think about it as a way of pattern matching. In the previous template, basically, the authors has defined several templates. Now the question here is that how do we match a piece of code conforming to this template, right? So suppose we want to check the reference bug. So there must be in the correct version of the code, there must be a code to check whether this variable is none, and if it is none, and if it is not none, it will try to dereference it, right? So basically, it is kind of a pattern. So how do we match the pattern? Here it proposes a AR parser to do this. I think for these presentations, we will not go deep into how AR parser work, but if the readers and audience are interested, you can go in it. Basically, it's the pattern matching problem. Here is going to see they have already defined a template and a syntax. But anyway, this way, I just feel that it's a tricky part of the paper writing. So if we talk in natural language, we just say we define a pattern, we define a template, and then we match the code with the template, and that's all. But if we go to write an academic papers, we need to define the context-free grammars and writing to BNF format, and then we define error parsers. So this is more about the terminology terms. But when we have a presentation and have discussions, we talk in a simple way. This is simply a pattern matching problem.
Okay, get it. Thanks, Cheng. Thanks, Dr. Lin.
Okay, let's move. Yeah, is there any question here? Okay, if there are no question, let's proceed.
Okay. So next, the syntax matcher will create the AST using the Cheng lib tool. So it provides a way to create the AST. So the AST provides a visitor pattern. So what this allows us to do is to create specific methods for each type of AST node, like an if statement, we can do certain things, or while statement. And so this allows us to specify only to check for certain
Yeah, I
statements.
just feel weird. they put the implementation details in the paper.
Oh, they wrote a lot for implementation.
Yeah, this is usually it's not that audience friendly if they put on too much details.
Oh.
But anyway, so I have a question here. Anyone know about the visitor patterns? So this is one of design pattern, right? So in software engineering, if you have some software engineering courses, have you ever learned the visitor patterns in your design pattern course or the course of object-oriented program design?
For mine, they didn't teach it.
They didn't teach in NUS.
But they didn't teach a visitor, I think. From the courses they taught command pattern, but not visitor.
I see. So you learn factory patterns, maybe strategy patterns, but not some pattern else.
Visitor,
maybe observer pattern.
Yes. Oh, yeah. I learned it.
Yeah. Anyway, so I think visitor pattern is a way for us to visit the graph and a tree in an elegant way. But so it makes no big difference in this research paper, and we can use anyway to visit the certain types. And I think you find, have you used AST visitor patterns before?
Yes, I used it before.
Okay, that's great. So anyone, if you have questions how to use visitor patterns to traverse the tree, and you can talk with Yifan offline. So we do not put too much time here. Maybe you can move on.
Okay, sure. Okay, so basically the syntax matcher will start the state machine once it encounters the if while for statement. And once it visits all the children of the statements, if or for, we will check the results from all the state machine forks, whether they return any matches, like abort pattern or exact pattern. And then we will also track the variables that we need to track in a JSON file as well. So this is the simple. Yeah.
Okay.
So now I'll talk about reachability and dependence analysis. So it will check for two things, which is whether the execution can reach the bug injection site. So this is the reachability from entry point to injection site. And we also check whether the variable dereference data is part of the injection site as well. So they used a code analysis framework called FIXREVERTER. So FIXREVERTER provides a interprocedural control flow graph. So because it's a control flow graph, we can get the reachability. We can solve the reachability problem. And FIXREVERTER also has a taint analysis module, which allows us to do the taint analysis from uncompressed buffer to the crash site.
Sorry, I need to stop here. It's better for us to understand more of the technical details, or at least the technical terminology here, especially for the students who do not have strong background in probe analysis. So, David, are you still there? So do you know what is taint analysis?
NUS. Oh, sorry, I haven't heard about it.
And you know about control flow graph? Do you know
Yes.
about it? And do you know what is inter-procedure CFG?
Then I don't have idea of that. I know.
Yeah. So in this case,
Cheng,
Cheng, you can help explain a bit. But anyone who is familiar with CFG and taint analysis. Okay, so if there's no volunteers, we can, Cheng, you can explain a bit about what is inter-procedure CFG.
Okay, sure. So my understanding of inter-procedural CFG is we connect the control flow graph between different functions. So we have a main function. We also have this BFD elf make section from, sorry, I don't know how to, but this is another method. So basically link them in the control flow graph. It's not just a single method. So that makes it inter-procedural because we link them through the entire code.
Yeah, in short, so CFG is basically for a single procedure. So for a given method, we have the control flow graph. But for some instruction, this method may call the other method, or this method may call by the other method. That's called a callee and a caller relationship. So we want the inter-procedure, we want the control flow graph to capture those inter-procedure instructions. Then we have an inter-procedure CFG.
Okay.
So the ICFG is to connect different caller and callee relation.
Yeah, exactly. Yeah. So which means that the nodes and the steps and the lines of code can be connected. The control flow of the lines and instructions in different methods can be constructed.
I see. And how about the word analysis, taint analysis?
Yeah, and for taint analysis, maybe I can briefly introduce. Taint analysis is that suppose it's more like sensitivity. Usually we're using sensitivity analysis for taint analysis. The basic idea is that we want to, I think it's fall into category of impact analysis. That is, if we change the input a little bit and we want to see what is the relevant variable will be influenced. So it's more like the inference function in probe analysis.
So it's just to test what variable are affected by the changing input, right?
Yeah, so usually we have taint analysis, usually have a source and have a destination. We want to see whether the change of the source, whether the change of the source variable will influence the value of the destination variable.
Oh, so to check is there any connection between these two variables?
Yeah.
I see. Okay.
Okay, let's move on.
Right, so for reachability, their implementation is first to take in a set of entry functions. Then from the entry functions, they will create the ICFG. And they will just check if there exists a path from the entry function to the injection set. And for taint analysis, they will check so previously I mentioned about the track terminals that the syntax matcher will find for us. The track terminals that are used in for instance, the object equals now. The object will be the track terminal. So we are tracking that, and we want to use taint analysis. So the object is the source, and we want to find whether there is some variable later that will be dereferenced. So for instance, reading, writing of the object. This is also reading the object, and also whether we are calling a function with the pointer.
So which means that only looking to the tainted variables. If the variable is not tainted by the input, they were not looking to it.
Yes.
Yeah, I think our approach, do you remember our approach? We just care about the executed program, right? So given a program, given input, if we execute it one or twice, So we can definitely know that they are reachable. Right. So if a code can be executed, then this piece of code will definitely be reachable. And then we modified it. So we definitely make sure that the variables and the statement will be tended. Right.
Yes. They're using static analysis. So
yeah, but anyway, they're using a more heavy-weighted approach. It will be very useful for the papers, but I'm not sure whether they're really that effective comparing to our approach.
Yeah, this results in overestimation as well. So
okay, no problem. Let's move on.
So this also implementation details, but they basically face some challenges when trying out phase-out. So some issues are like phase-out did not track specific fields of objects.
Yeah, actually we don't go into that details. Let's move on. Yeah. So there's a lot of the proof analysis to ensure that the place is reachable. And so let's move on to the next. Yeah.
Okay, sure. Okay, so now we reached a bug injection stage. So we match the syntax, the code injection sites. We also figure out that the injection sites may lead to crashes based on the taint analysis and the reachability. So first, I would like to talk about some states that they define for bugs after fuzzing. So after fuzzing, a bug might not be reached at all. It might be reached, or it might be triggered. So there's a difference between reached and triggered. So reached just means that it executed the if statement, for instance. Then for triggered, only the condition that we remove must be true, while the other conditions in the same if statement are false. So triggered is more likely to result in a crash if we remove that if statement. And also, when we are injecting bugs into the code, we also want to inject a mechanism to detect these states. When we run the fuzzing, we want the code to print statements that tells us whether the bug was reached or triggered when we inject the bug as well, which I'll explain later. So the way they, this is also implementation detail, but the way they detect whether a bug was triggered or reached is to use a macro. So they create a macro called FRCOV, and if it is defined, it will print out statements whether the bug was triggered or reached. So if the FRCOV, it will log the statements. Otherwise, it's just a bug injection. They remove the if condition entirely. So this allows us to toggle the reached, triggered, or reached detection. So for the actual injections, they will for abort pattern, they will remove the object equals null. It will become like this. For execute, we saw this example before. So they will loosen the condition by removing the symbols, because symbols was used in the body. So they remove the symbols not equals to null and become the red one. And for assign, they'll just set the condition to false. So the assignment never occurs. And so once they inject all the bugs, they will compile it with address sanitizer and undefined behavior sanitizer turned on. So what this allows the code to do is to crash whenever we have temporal or spatial violations. So for instance, we read after free or buffer overflows, these will cause crashes. So we can definitely detect any crash or any memory errors in the code. And the final part of bug injection is to do a bug filter. So they want to filter any bugs that are too easy, because we want to compare different fuzzes, the better and the worst ones. We don't want to test them on easy ones. So there are different ways to implement this, but one example they provided was to inject bugs one by one. We inject one bug and then we run all the test cases. And if any of the tests fails, we won't use that bug, because it could mean that the developer already considered.
And where are the test cases? And how do we get the test cases?
This has to be provided by the source code.
All right.
Yeah, there's another way to do bug filtering without test cases, but I'll go through that later. So the last part is the root cause detection. So the rationale is that if the program crashed and bug X was triggered, it does not necessarily mean that bug X was the cause, because we injected many other bugs. So we need to determine the exact triggered bugs that caused the crash. So first, they separated the possible crashes into 2 different causes. So individual cause is just a single bug A is sufficient to cause the crash. And combination is we need at least 2 or more bugs injected to cause a crash.
And here the question that why don't we inject the bug one by one?
They talked about some fuzzers using taking advantage of bugs changing control flow to cause crashes, which requires a combination of bugs. So they want to test fuzzers that know about this.
But it is okay. So given the programs, we may inject 100 bugs, right?
Yes.
So they want to, okay, that's okay.
Okay. So this is the algorithm, but I'll just talk about the summary for finding the root cause. So the summary is actually a brute force algorithm. So they just try every combination of, okay, so first we take a capital I input first. A has to crash the program. So once we have an input that crashes, we will also have the set of triggered injections. So once we have these 2, we can run the algorithm. So we will just try every possible combination of the triggered injections. And we will see if running capital I on it, the input, does it crash? If it crashes, we'll add it to the result. But the catch is that if a subset, so let's say we're testing a set S of bugs now. If any subset of that set S already is in the result, for instance, we're testing A, B, C, and AB is already in the result, then we don't need to test A, B, C. AB is enough to cause a crash. So we won't add A, B, C into the set of combination results. So this is the triage algorithm. Okay, so that was the end of the FIXREVERTER. So now I'll talk about RefBugBench. So RefBugBench is, they created 10 target programs that had FIXREVERTER run on it to inject bugs. So we can use these 10 programs to test fuzzers now. So 8 were taken from Google's fuzzing benchmark. And also 2 are taken from binutils package because they were often used in the fuzzing literature. This is also an implementation, so I think I'll skip this. I think I'll skip, sorry. This was implementation. Okay, so now we reach experiment. So they wanted to answer these 3 questions. So whether the triggered bugs actually cause crashes, whether the bugs are too trivial, they want them to be difficult enough, and whether the fuzzers can find combination causes. So they ran on these 5 fuzzers, and they ran on the 10 projects in RefBugBench 3 times each, and with a timeout of 24 hours. So MetaFuzzer firstly is upper bound of all the results from all the fuzzers. So this means that, so for instance, total here 638 means that in total, all 5 fuzzers, they detected 638 unique triggered bugs. So that's what it means. This is the result of all 5 fuzzers. And this is the programs on the leftmost column. And it detected 219, the 5 fuzzers detected 219 bugs out of 2,565 possible bug sites. And most of them were abort patterns, the guard clause, if object equals null, return. So most of them were those. And
by the way, so if I understand it correctly, there's only 10% of the bug has been reported by those fuzzer, right?
Yes.
But it also need to prove that whether the injected bug is really reachable. Have they provide kind of evaluation?
All of the reach and triggered bugs that they injected already passed the static analysis, the reachability and.
No. So if there's a pass, it cannot guarantee it is reachable. For example, I have 2 conditions. The first condition is x greater than 1. The second condition is x is smaller than 0, right? There are definitely a control flow there, but we know that the constraints will unsolvable.
Yeah, they didn't talk about that. I think they.
Yeah, so I think for security conference, the papers, I don't know how the authors think. They're not that expert. They're not that experts in program analysis, I guess. Okay, let's move on. But they do not, anyway, they do not provide evidence that the injected bugs are really triggerable.
No, it's a over approximation. Yeah.
Okay, let's move on.
So from the experiment, AFL++ was the best. It detected the most individual causes, and it detected the most bugs in 6 out of the 10 programs. Then Eclipser was second, and AFL Lead Fuzzer, FFuzz found much fewer, but all of them detected unique bugs in at least one. Detected the most bugs in at least one program. So this is a chart of number of individual causes detected over the 24 hours timeout. So from the graph, we can see that at first they find bugs really quickly, then over time it slows down. And after 12 hours, some fuzzers were still able to detect new bugs. And one interesting point that the researchers pointed out was that Lip Fuzzer beat many fuzzers at the beginning, but it slowly lost out to other fuzzers. Okay, so whether the bugs are hard to detect, which also means whether we can use FIXREVERTER to test the programs. So the fuzzers, so this I mentioned before, they detected 219 bugs out of thousands, and the researchers believe that this is sufficient number of bugs to differentiate the fuzzers. And they also said that with a longer trial, more bugs could also be detected to further differentiate the goodness of fuzzers. So this is a Venn diagram of the different bugs that they found. The different the fuzzers found different bugs here. So one interesting thing is that a large number of the bugs were detected by all 5 fuzzers. 40% actually was detected by all 5, and 16% was detected by 4 out of 5 fuzzers, and 19% could only be found by an individual fuzzer, just one fuzzer. So each fuzzer could find their own unique bug. And AFL++ found the most, so 28. And for the last question in the experiment, so many crashes turned out to be due to a combination of bugs. So this is because the first bug changed the control flow to a second bug, which caused the crash. And the researchers did state that individual causes is easier to differentiate the fuzzers just by looking at the number of bugs they found. But it doesn't account for certain techniques that fuzzers may use to cause crashes. Like they might take advantage of bug interactions. So combination causes might also be important to differentiate the goodness of fuzzers. But those fuzzers that found a high number of individual causes also found a high number of combination causes. So AFL++ was the best in both metrics. And also better fuzzers tended to have a higher number of reached and triggered bugs as well. Okay, so this is my last slide. So some takeaways. So FIXREVERTER is, in summary, a new framework that injects realistic bugs by using existing CVEs, and it can be applied to any real-world program. And also, the bugs also provide a unique indication whenever they are triggered. So they use the macros, which I described earlier, and we can also use the triage algorithm to find the root cause. It also prevents overfitting because we can always apply on new projects and we can specify new patterns to create new bugs and new benchmarks. And also the bugs were high enough to differentiate the different fuzzers. Yep.
All right.
So that's the end.
All right. Anyways, this work is kind of inspiring, but it could be better. There must be a better version for that. You know, so in software engineering, whatever software engineering security, we always sometimes when we we are always exploring the frontier of the area, right? So the more we go for the further we go, the more likely we need a benchmark. So this work gives us a very good example. So once the area, for example, such as flooding and testing has been quite developed, so there's a need and there's a call for the benchmark. And usually we don't afraid of whether we follow the pattern of writing a paper. We look into the most important question. I think this paper definitely have flaws. For example, their claimed reachability is not the actual reachability, at least from sense of analysis. And the patterns seems very limited, despite this paper writing maybe well framed, we have good stories, but definitely it cannot be considered as a perfect. Nevertheless, it is still the distinguished paper, right? Hello, Cheng.
Yes, a distinguished paper.
It's distinguished paper. So which means that it's time for important problem. As long as the problem is important, we don't care some minor flaws because this work will definitely facilitate the area. Okay, so is there a question for this work? Any questions? Everyone else was encouraged to raise a few questions after the discussion. Okay, if there's no question, let's call it a day. Thanks everyone for the attendance. Yeah, see you next week. Bye.
Thank you, Prof. Thanks, everyone.